Good evening, everybody. Welcome to the first BrisScience of 2020. Thank you for coming out on this rainy Brisbane night. I am going to be your MC for this evening, Joel Gilmore, and of course you are here for BrisScience, Brisbane's free public lecture series on science, where we bring not just the best scientists, but also the best communicators to share their passion for science and research with you here in the wonderful Brisbane audience. This series, of course, produced by the University of Queensland and hosted at The Edge at the State Library of Queensland, our wonderful venue partners, who have lots of other fantastic activities you can check out on their website. I'd also like to start by acknowledging the traditional owners of the land on which we're meeting tonight and to pay my respect to elders both past, present and emerging. A couple little bits of housekeeping before we get started. We are, of course, going to have our speaker, who I'll introduce in a moment. Afterwards, we will be taking some questions. And at BrisScience, we do these questions via Twitter. So if you have a smartphone, you can use the hashtag BrisScience and ask away. Alternatively, you can go old school and you might have picked up a question slip on the way in and you can write down your question and we will come around and collect those questions at the end. And I will get to as many of those as possible. Finally, though, if your question doesn't get asked, there will be an opportunity to have some one-on-one chats afterwards. We'll have some food and drink outside, and we'd love for you to hang around and chat with our speaker and also amongst yourselves. It should be a cultural experience, just like going to the theatre. It's what we want from BrisScience. So hopefully that'll be everything there. And we'll be live tweeting throughout tonight as well, hashtag BrisScience, so you can follow along there if you miss something or want to catch up later. We'd love for you to retweet those. All right, I think that is all of the important housekeeping. So this is, of course, our first talk of 2020, and so we thought we'd get back to our fundamentals, to the only true science, which is physics. And no, I don't have any personal bias here, obviously. At BrisScience, of course, we are all about reducing ignorance. And we, of course, have a standing open invitation to all of our political leaders. Be funny if it wasn't true. But tonight we are actually going to revel in ignorance, looking at how ignorance in the quantum realm, the absence of information, might lead to new, potentially world-changing technologies. And to take us on that journey, I'm very excited to introduce our speaker tonight, Dr Jacqui Romero, who is a senior lecturer and Westpac Bicentennial Foundation Research Fellow at the University of Queensland, where she researches quantum information in the Quantum Technology Group. She's also the recipient of one of just 15 L'Oreal UNESCO International Rising Star grants in 2019. Just 15 available worldwide. So we are truly in the presence of excellent research tonight. And so tonight, I think that's all I need to say. Sorry, just checking my notes here, I'm a little mixed up. So please put your hands and welcome together our speaker for tonight, Dr Jacqui Romero.
Okay, thank you very much for coming over in this very good day for the ducks. We don't have that often in Brisbane. I'm really glad to see all of you here. A little bit nervous. This is just my second public talk. The first one was on a different topic. Why I changed the topic, I don't know. This is just really more interesting. Ignorance in a quantum world. So I am part of a Center of Excellence for Quantum Research, the Engineered Quantum Systems. And over the years, I've also been funded by the Australian Research Council. So I came to Australia for an 18-month contract. Quite risky thing to do when you have a family, but sometimes it works out. I got a fellowship from ARC, and then I moved on to Westpac Research Fellowship. And I also have funding from L'Oreal UNESCO for Women in Science, as Joel have said. So, yeah. So as I've said, this is my second public talk. The first one was for Pint of Science. And when they asked me to speak, they gave me these guidelines here to, make your talk personal, make it personable, and avoid tables and graphs, which if you're a physicist is really hard. So I have to apologize. I really cannot avoid the tables and graphs. But if it doesn't make sense, just move on. It's okay. We can have one-on-one if you're really interested. Okay, So I show this picture here because maybe that's still the picture of a physicist in our heads. And our corridor in our department is littered with pictures of these people. They don't look very happy. But this picture here, mind you though, probably has the densest population of Nobel winners, like pretty much every other person in this picture from the 1927 Solvay conference. Did I pronounce that right? Solvay conference? Every other person probably has a Nobel Prize, like Marie Curie here even won 2 in physics and chemistry. So that's what maybe physicists' image in our heads was for a long, long time. And then came Big Bang Theory, which totally changed the picture of a physicist, right? For better or for worse, you decide. But we have this diversity now of a picture of a physicist, so maybe that's good. Well, this is me, so that's actually the first day of my PhD. Like October 1, 2008, in sunny Glasgow. So that's the first day of my PhD. This is me on my graduation day. So I took a photo in front of the workhorse of my PhD. So that's my experiment over there. I love it very much. It's probably all destroyed now by the future PhD students, but I had lots of fun there. And then I moved to Australia. So as I've said, I'm part of EQs, and in EQs, every couple of years, we have this shorts films festival. So if you're a filmmaker and quantum physics inspires you, you can submit short films, and then we screen them during World Science Festival, or we find time to screen them. And I was one of the judges and panel in one of those years. And I also have, in the midst of that all, I also have a family, so I have 3 kids. So I just show this here because we still have this idea that, a science career and family, personal life, they may be mutually exclusive. So existence proof, at least, that, it's not impossible. And if you won't take anything else from this talk, if you turn off when I start talking about quantum physics. This is the most important message that I really want to get across, that it takes a community to raise a scientist. In physics, there's not very many women physicists, and I consider myself lucky because I'm still here. And I am here because I was raised by really supportive parents who really didn't say, you're crazy, what would you do if you become a physicist? So it's really a change of behavior, I think, that we need so that we can have more scientists, more women scientists especially. And of course, I went to really liberal institutions where, your dreams are not crushed. I got a lot of goodwill from the people around me. And I'm really very grateful for that. So I'm passing that goodwill forward. So last year, I started a research group in the School of Maths and Physics. And it would be obvious later on why I'm calling it QDITS at UQ. I have a small team, and we have a website. You can go to our website. It's all pretty basic. But I'm so excited to have started this research here in UQ. So hopefully you'll hear more about what we do in the years to come. Okay, so this is the plan for my talk. I will discuss what the difference is between classical and quantum information. And then I will move to an experiment that we did at UQ, which hopefully drives home this difference. And finally, I will situate ourselves, where are we in terms of quantum technology? And hopefully, that's interesting too. Okay, so first part. Who here is really interested in quantum physics? You've read quantum physics books, the popular ones. Okay, that's good. That's really great. Okay, so I am going to approach quantum physics with what I think is the minimum. So I won't start with the really weird things. I will start with really simple things and hopefully build up I don't know, the weirdness, the special features. So, okay, let's start. So when I get asked what is the difference between quantum and classical physics, I actually still, I don't know. I really don't know. But what is obvious to me is that the information as we view it in classical physics is very different from information in quantum. And that is a really important key for us to understand, I guess, what the difference is. So I want to start with information. Like, what is information? Like it's when I was younger, when I was a high school student, I got my first computer when I was 16 years old. And information then in my computer would be essays or worksheets or something really boring for school. But now information is just suddenly so important because all of a sudden we tell our lives out there, right? So and then we can manipulate information. We have fake news now. And so over my, my adulting, this idea of information has actually changed. It's all of a sudden so much more important now. But as a physicist, what really interests me is that, this information, at the very bottom of it, it is a physical information. There is something that you need to carry that information. So for example, when I was young, I played those, the CAN telephones with your playmates. You connected by a string, you talk to each other. And if you look at that system, really what happens is that the vibration of your vocal cords, it gets transmitted through the string and onto the ear of your friend. And then it vibrates the eardrum, and then somehow the message gets sent, right? So there was a physical system that mediated that information. So information's like that. There's a physical system. So what the previous example is an analog kind of information, but these days we talk about digital information. And there's really nothing special about that. It's just that we made it into high or low. We've made it two values, 0, 1, okay? But still information. So that is actually the simplest classical system that you can have. It is a two-state system. So that's why we call it the bit. But then you think to yourself, well, a coin is a bit, right? You have heads and tails. You've got the two states there. And if you want to introduce some kind of abstraction, as we do in quantum physics, we call it +1 and -1, your spins. So that's, again, a two-state system. If you want to imagine a physical system that you can associate with that, maybe you can think of electrons or atoms, spinning. So these two systems here are what we call qubits. And really, this one is actually enough level of abstraction for us to understand what quantum information is. So what I'll do is I will do experiment with these things here, what I call spins. Okay, so let's do experiments with spins. So imagine you have a spin and you don't know what that spin is. That's your system. But you have, okay, so let's review something first. So a spin, you can imagine, maybe you can imagine it as a vector. So a vector, you have both magnitude and direction. So velocity is a vector, right? You have 10 kilometers per hour forward, right? In any direction you like. So that's a vector. And a vector has components. So I can go to the stage this way, diagonally. So I will have component in this direction and this direction, doing volts now. So it's just, so the vector components are just what is the projection, what is the shadow that this vector casts on a particular axis. Okay, so that's the component. So the spin is something like that. You can think of it as a vector. So I have an apparatus now. It has a little direction. It says up, okay? And this apparatus measures the component of the spin in this direction here, okay? So I do that experiment, and then I see that the result is +1. So doing this experiment, I see the spin is like that. It's up. It's in the Z direction, okay? Then what I'll do now, I'm going to rotate that experiment, that apparatus, the other way around. So I flip it. And what I observe is that the +1 now becomes a -1. And that's just consistent with the vector, right? Because if you were looking at something pointing up, but then your apparatus was, pointing down, then you pick up a negative sign. So far, so good. Yeah? Yes. Okay. So now, what we'll do, so given the result was a +1 when the direction was like that, okay, I'll just label that one as +1, okay? Then we'll do another experiment. I turn the apparatus, instead of up, I do that, okay? So let's guess. What do you think would be the component in this direction? So the previous experiment, we see it was +1. So what's the component now in this direction? 0? You think it's 0? Okay, so you do that experiment with our spins, and what you actually see is never 0. It is +1 or -1. It's always +1 or -1. So there's something special now, isn't it? Like, why? 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 So you expect it's 0 because that's how vectors work. But if you do that experiment, and quantum physicists have, we've done this experiment many times, we find that it's always +1 or -1, totally random. Totally random as in, if you were to count the number of times you got +1, it would be the same as the number of times that you got -1. So it's totally random. So if someone asks you to predict the results of experiment like that, I guess randomly. And that is the best that I can do. Like what we think of as ignorance in our, normal speak, like, what could be more ignorant than guessing randomly? Like that's about it. Okay? But in a quantum system like that, well, that's the best you can do. So, like, maybe quantum physicists don't look at it probably as special as I do, but I feel like ignorance is really special in quantum physics because it's the best that you can do. So in a way, it's knowledge, right? So anyway, okay. So in a way, like determinism, like you read all these, in my thesis, like nothing is real, John Lennon quote, right? So determinism, like reality as we think of it, it sort of breaks down. But it breaks down in a very special way because, as I've said earlier, it's just not some random. It has to be really random. Like if you take the average of your sigma x, it has to be 0, just as you expect in a classical vector. So the average, if you look at the average, it's a classical vector. But shot by shot in that experiment, it's random. Okay, so so how do we explain that in quantum physics? Well, it's very hard. And I don't think people have agreed how we explain it. That's why we have the quote, shut up and calculate, right? Just shut up and calculate. It works. I mean, the simple explanation is that experiments are never gentle. So in quantum physics, you have a system and you have an apparatus. And somehow, by interacting that apparatus and your system, something gets disturbed. So it's not like our classical experiments where it's almost trivial to do experiments. Like like there's like a barrier. Like this is your apparatus, this is your system. In quantum physics, it's very complicated. It's like your measurement disturbs your system. And also, of course, maybe you've already realized, spins, they're not vectors. They're not classical vectors. They're very peculiar vectors, and I will explain that later. Okay? So that's, I guess, the minimum. If you are happy to accept that spins behave this way, that's already quantum information. But now we make our classical information break down more. Because so all our computer science, it's based on Boolean logic, right? And or you have propositions, you do whatever, right? So for example, proposition A, the speaker is wearing a blue shirt. You can assign a truth value to that. And that's 0 because I'm not wearing a blue shirt. The speaker is wearing black shoes. Yes, I am wearing black shoes. So I have 2 propositions here with these 2 truth values. Okay? And then I'm going to operate on them using Boolean logic, say AND. Okay? So A and B, 0 and 1. So 0 and 1. So A and B has a 0 truth value. Okay? So even if you repeatedly do that experiment, like say you close your eyes, you open your eyes, you look at what shirt I'm wearing, what shoes I'm wearing, you can do that ad infinitum. The value of the proposition A and B will always be 0. Okay? So now let us apply that to what we've learned about spins. Okay? So say, for example, your proposition are these 2 things. Okay? So as we've, let's say, the proposition A is that sigma z is 1. Proposition B, sigma x is 1. Okay? So you do that experiment. So how do we test that? So you do your experiment, you say +1. When you measure z, so A is true. Then I do my experiment on sigma x. I see that it's +1, so B is 1. So A and B now is 1. So remember, it's only 1 if both of A and B are 1. Okay? But then, an experimentalist, should always repeat the experiment, right? So I repeat this experiment. And now, I measure +1 on the z. I repeat the experiment for sigma x, and I measure a -1. So my proposition B now is 0. So A and B now becomes 0. So what happened was, if you apply your AND to these 2 propositions, you will get 1 or 0, like just randomly. So you cannot do Boolean logic on the spins. We have to do something else. We have to do quantum information with them. Okay? So there is actually something hiding there. Like maybe those who are really aficionado would have predicted this. Okay? So how about if your proposition is that the particle is position x in a position x, and the proposition B is that the same particle has some momentum, moving right, moving left. Okay? So what if these are your 2 propositions? The conjunction would be the uncertainty principle, right? So suddenly you have these 2 statements here, and you cannot confirm this statement here because you've got your, so it's not confirmable, therefore it's meaningless to me because I'm an experimentalist. So that's your Heisenberg's uncertainty principle. You cannot say in quantum physics that you cannot say that a particle, that my car is stopped at this red light here, Oh, no, not, okay, wrong. Okay, so you cannot say that your car, that your GPS, so in your car, like you have your GPS, your car is here, and it's moving in a particular direction. You cannot know both. Okay, so that's Heisenberg's uncertainty principle. And you can already get a feeling of that when even just looking at spins. So, yeah, if you ask me what's the difference in quantum physics, so again, experiments are never gentle. And quantum states, they are peculiar vectors. Peculiar in what way? Because quantum states are described by complex numbers. So remember, in classical information, you either have 0 or 1. But in quantum physics, you can have superposition of them. So it's like they're both 0 and 1. And alpha and beta, they are complex numbers. Like complex, like life, it has real and imaginary parts. Okay, so it's really, yeah, the magic comes from those complex numbers. Okay, so I guess that's all those things I've told you. I've read that in this book, like quantum mechanics, the theoretical minimum. And when I first read it, I thought it was very, very minimalist. Like, it's really minimalist, because usually when you read about quantum physics, like when I was 15 years old, I heard my physics teacher say that he hates quantum physics the most. So what I did was I Googled what quantum physics is. And all of a sudden, all these strange, words like entanglement, cat, dead and alive. It's so weird. You usually don't start with the really minimum, which is the spins. And I thought, oh, this is brilliant. I'll give this in my talk. So if you're interested, you can read this book. It's really good. Highly recommend. Unfortunately, when I went to university and learned quantum physics, we actually started from the levels of the hydrogen atom, which was totally, a bit boring. And I think it really removes the magic. I think if you approach quantum physics from information perspective, as we did with the bits and the qubits, X, Z, I think it's really, you can get more people into it, because then you start with something familiar and then move on to the unfamiliar. Okay, so that's the first part of the talk. So the second part of the talk is an experiment at UQ, which hopefully would show you how different it is. But first, we have to answer this question, how to make quantum states. So the quantum states, you can make them from trapped ions. So an atom is neutral, but if you strip it of a proton or an electron, you have an ion. And nowadays, we can trap them in a line, like, we have really good control. What we see in the news a lot are superconductors. And we can also do atoms. So like this Mona Lisa picture here is actually atoms, a cloud of atoms, the width of your hair. This is 100 microns here. We can paint any picture we like at UQ. Not me particularly, but at UQ. So we can make atoms do whatever we like. I personally like to play with light. And light has many different properties. So one, for example, is polarization, like the plane that it vibrates. So it's your equivalent to your bit. Like if it were vibrating this way, that's 0. This way, it's 1. So it's 2 states. So polarization is qubit. You can also have color. So just how energetic that photon is, that's also a quantum state. And you can have time bins. Like if you have a detector, when did the photon arrive? So like it's clicks, time bins. So I work with the shape of light. Like, have you ever thought of light as having shape? Maybe not, no? So usually when you buy yourself a laser pointer, it comes with a very circular, bright spot. That's the laser that we have. But actually, you can shape light into anything we like. Like, just forget about the names. I just put that there, so you can Google them later if you're interested. But we have a lot of shapes, and I really think of the shape as an alphabet. So what do I mean by that? So this is your quantum state. You have your 0 and 1. And I can choose particular shapes as my 0 and 1. So I can create this superposition here. That is your cat. That's both dead and alive, right? Like, you choose 2 of those shapes, that's your cat. Now, what is good? So those are qubits, okay? So what is good about the shape of light is that, as you've seen earlier, you've got plenty of them, right? You don't need to just work with a cat. You can have the whole zoo, if you like, right? So if I want to have more than qubits, I can have them. I can have all the other shapes just stand for whatever ket or bra I want, right? So those are qubits. So they're called qubits because it's the possible values. Okay? So that's why I call my group qubits at UQ, because we deal with qubits, not just the 2-level quantum states, but many-level quantum states. So it took a bit of work, actually, before this was accepted in the quantum community, that shape is really, quantum. So I'll just list all the papers here. So I don't have time to discuss each of them. But the conclusion is that shape is a quantum carrier. It's a carrier of quantum information, and we can use them. So I used it for an experiment in my group. So again, that's my group. And the experiment I'm going to tell you about is work I've done with Michael, Sally, and Andrew. So we haven't published it yet, but it's going to be published soon. It has an interesting story. So I saw a paper in Physical Review Letters. So Physical Review Letters is quite a prestigious physics journal. Einstein published there, okay? And it had a cartoon. So it was the first paper I saw with a cartoon, and it had an intriguing title. Does ignorance of the whole imply ignorance of the parts? Just ignore the second part. I just put that there for, that's not the abstract, that's just the title. But I don't have time to discuss the second part, so let's just, okay. So in 2011, I saw that paper. I wanted to do that experiment in Glasgow, but my supervisor wasn't interested. So I wasn't able to do it there. And I'm so happy that I wasn't able to do it there, because when I came to UQ, I actually met a philosopher turned physicist, even better. And she was able to explain to me this, this whole thing, and it's just so much more interesting than I originally thought. So I guess that's just, yeah, I mean, I'm lucky I'm not working in COVID, right? So where I have to produce results right away. Here you have a project which took 7 years, 8 years before we were really able to implement it, and yeah, it's part of the fun of being a physicist. I get to linger on the things that really interest me. Yeah, so sorry to the immunologists I don't know. So I was so excited. We submitted that paper, and then here comes referee A. I miss a punchline. Blah, blah, blah. The mathematical, physical concept has been presented in papers before. The experiment's not special, not pushing limits, blah, blah, blah. So that's just what we deal with. So when we get reports back, you have to answer it. You have to decide, is it worth fighting for or not? Do you go to the next journal? So we decided we'll go back and we'll answer all the questions, and the same referee sent this back. And I so love it, I'm going to underline it, every word of it. So I read the article again in detail. I wonder whether they actually read it before. And yes, it's actually unique. It's a very nice real-world interpretation of a statement which is usually not particularly accessible to non-experts. So when we got this, I thought, oh, I'll talk about it in BrisScience. Let me test that. Okay, so let's see. So going back to the title, whole, does ignorance of the whole imply ignorance of the parts? So first, we have to identify what is a whole and what is a part. And in quantum physics, when we talk about wholes and parts, it's usually always entangled pair. Entangled pair is like you have these two particles, you send them to opposite parts of the universe, say maybe just the lab to be realistic, okay? Opposite parts of the lab. And you have complete certainty of the complete state. Like say, for example, you always know they will always be both spin up or both spin down. So you have certainty on the whole state, okay? The correlation you're sure of. But if you look at just one, it's completely random. Okay, sounds familiar now? It's just like the experiment earlier, right? Sigma Z, sigma X, so it's usually entanglement. But, yeah, okay, we're done with that. So in our experiment, we used not an entangled pair, a good old dit string. What is a dit string? You have Y, and it has two letters, Y0 and Y1, and each of these has D possible values. So it's a dit string. And how does D come in? So as you make D larger, the randomness increases, right? In what way? Say you imagine, right? If you have a 12-sided die, throw that away, it gets harder to predict what face it lands up, right? And as the number of faces increase, it's harder to guess. So the system gets more random, okay? So D is our proxy for randomness. But then how do you know if something is random, right? Like perfect cartoon for randomness, okay? You have to test many, many times. Like that's the thing with randomness, right? You're never sure. You have to repeat ad infinitum. Okay. So that paper with the cartoon has this mouthful of an inequality, which I'll show here. I'll just put that there. But I will not discuss the whole inequality. I'll just put it in the context of our experiment because I think that's easier. So the scenario is you have a student and you have a teacher. And you have a cheat sheet, okay? So here, E. So the inequality, which I've taken out now because it's confusing even to me. So there exists a pointer C that points to a part where the student has large ignorance. So if you were a teacher, you can always design a test that would reveal which part of that dit string your student doesn't know, okay? So that's true for classical information. So then the game for our experiment can be framed in terms of a task. So the teacher's task, find a C that points to the part that the student doesn't know, okay? That's the game. So in terms of probability, this is how it looks like. So you have your dit string, Y0, Y1. So think of it as like 2 pages in a book, okay? So you have your set Y0, set Y1, and you have different instances of the small Y0, Y1, okay? You have D possibilities for each page, so you've got D squared of these. Now, in that exam, I haven't told you yet, but there is a knowledgeable friend who gives the student some cheat sheet, okay? So the student comes to the exam with a cheat sheet that is a dit, okay? It can only contain D, whereas the dit is 2D. You have D times D, okay? But the cheat sheet is only D. And then the teacher would ask a question, okay? So the student can get it right or wrong. So the theorem, when you cast that in terms of this guessing probability, looks like this, okay? There exists a pointer, 0 or 1, to denote the two parts, such that the guessing probability is less than 1 over square root of D, given that the student had the encoding E and the teacher asked part C, okay? So don't let this intimidate you. It's just a way that we write probability, okay? Guess part YC such that, so that's what that means, such that the student had E and the teacher asked question C, okay? So now let's think about it. What is the optimal strategy for the knowledgeable friend, okay? So the optimal strategy is we always encode one part of the string, right? So then if the teacher asks about the Y1, you get it 100% of the time. But if the teacher asks the other part, well, you guess it randomly because your cheat sheet was not that part. Okay, so that's your optimal classical strategy. So it's like you've got a best and worst guessing probability. So in order to spot the student's ignorance, what the teacher has to do is just find the part that is guessed at random. So what part is the student guessing 1 over D of the time? And that's where the ignorance of the student is. Okay? So far, so good? Okay? Good, I'm getting nods, that's good. Okay, so, and also note that 1 over D is actually less than 1 over square root of D, so all good, this inequality is satisfied. Now, let's look at the quantum strategy. So the quantum strategy, let's introduce Einstein as our knowledgeable friend. So the quantum strategy is you encode, you still have D levels, but you encode this quantum state here. I just put that here. I know it's ugly and intimidating, but I just put that here because it has X and Z. Again, going back to your spins, X and Z. Okay, but I take that away now. I replace it with this beautiful picture here, because this really is what the encoding is. So if you have a three-level string, so three letters of the alphabet, this is what string 0, 0 looks like. This is what 0, 1, 0, 2. It's really, yeah, they're pretty. Okay, so this is my quantum encoding using the shape of light. This is for just D, for 3D. We can also do 7 and 11, and we actually am able to create that in the lab. So that's actually from a camera in front of our experiment. So we can do it. So that is my qubit encoding for my 2-dit string. Let's see how much better that works. Or does it? Yeah, well, I already said so. It will work better. Okay, so the quantum strategy now is you encode this one. And the guessing probability, if you calculate it, so now the student is given an encoding, which is, so this one is just this one. So the guessing probability now becomes these quantities here. So 2 things to notice. 1, the guessing probability is now the same. Okay? So it's like, what don't you know? Like you're just guessing them same number of times, right? So, and also, neither of them is guessed randomly. It's not 1 over D. So if you recall again the theorem earlier, well, we probably not, so I write it again here. So this is the theorem earlier. In classical information, there exists a pointer such that this is true. So this one is actually wrong, right? This quantity is actually bigger than this quantity. So the conclusion then is that if you use that quantum encoding, there is no pointer to the part that you're ignorant of. The teacher cannot find what part the student didn't study about. Okay, so it's like, in a way, the ignorance, it's hidden. Okay? And you can do that with a quantum encoding. So you can score. So I ran this talk, right, with our comms person in EQs, and she said, you know, I really didn't get a lot of that part. So it's really all right if you didn't get it. But this part, she said she understood. So run me again, the classical strategy. So you have 100% getting one part correctly, 1 over d on the other. So if I get my average grade, I get 75% for d equals 2. Okay? You get it 75% of the time. If you do your quantum encoding, again, this is my guessing probabilities for both parts. That's the average grade. I just multiply by 1/2 because, of course, half of the time the teacher asks why not, half of the time why 1, right? Okay. So for d equals 2, that's 85%. And whoo, there you go. You've got 10% difference, right? You've got an advantage when you use the quantum encoding. How about for higher d? Say d equals 6. So for the classical strategy, you get 58% of the time, correct? For quantum encoding, you get 70%. So it's a way to beat the teacher. If you use a quantum encoding, you can. So with a qubit encoding of a 2-dit string, 1, the student can get a higher score, and 2, the teacher cannot point which part the student doesn't know. So actually, the title of our paper, the one that we are trying to publish, it's Hiding Ignorance Using High Dimensions. And I think it's really a very accurate title. Yeah, I think it's going to be accepted soon. Yeah. Okay, so we're done with that. So now I want to just very briefly situate ourselves where we are in terms of quantum technology. So of course, quantum computing is very interesting. But we have to remember, quantum computers, they are not just faster versions of our laptops, okay? Quantum computers, they are quite special. They are advantageous for some very specific problems, like factoring. So this is Shor. So in the 1980s, he proposed an algorithm to factor very large numbers. And he showed that if you use a quantum computer, you can actually do it in much less time. There's an exponential speed up. And the other one is the Grover's algorithm. So this is if you have an unsorted database, you want to search it. With Grover's algorithm in a quantum computer, you get quadratic speed up. That's why Google's very interested. Okay, so I'll maybe focus on factoring. Why is that interesting? So factoring is interesting because it's a one-way easy problem. Like if somebody asks you to multiply numbers, like I did that in a minute, I timed myself. Okay, so you can do multiplication really easily. But if somebody asks you, what are the prime factors of that number, it's suddenly hard, right? And that's actually the basis of our encryption these days. We cannot factor large numbers. That's why when you put your PIN in that ATM, you're safe because no one, like in that encryption system with the bank, there's some large prime number there and nobody can factor that. Okay? Well, what are the prime factors of that one? That's the 2 numbers I multiplied earlier. That's the 100th and 200th prime number. Okay, so where are we at the moment? So we are still pretty much secure, okay? So this line here is the number of bits that NIST, the National Institute of Standards and Technology in the US, so they ask, so this is what they recommend to keep our keys secure. And these are the lines. Those are different estimates for a quantum computer with 2L² logical qubits. So that's actually a lot. Like this is about 2,000. Like we don't have a quantum computer with 2,000 qubits. So we're still pretty safe. But it doesn't mean we should be complacent. Because when a quantum computer arrives in the future, we can back-hack everything. So actually, what we have to do now is find a problem that even a quantum computer cannot solve. There are problems like that. So that's how you future-proof yourself. Well, the mathematicians do that for us. Okay, so the quantum computers today, we have trapped ions, and you've seen in the news probably, we have Google, 53 qubits, IBM 162053. This one's for the public, IBM Quantum Experience. You can Google that. But these are physical qubits, okay? What we need are logical qubits. So it's like you have a qubit, but then there are errors there. So you have to correct those errors, and based on estimates, it's like, I don't know, anywhere from 10 to 100 to 1,000. So we're really far. And there's a lot of companies working on that very important problem. Like the first application of a quantum computer probably would be simulation. Really, for me, it's simulation. Because if you have a quantum system you want to simulate, just make that simulate that with another quantum system. And it will solve the problem for you, right? So that's probably the first application we'll see. Now, this is more exciting to me, quantum communication. So quantum communication, this is where we're at. So we have intercontinental quantum communication via a satellite, MISHUS satellite from USDC in China. So in 2017, they were able to send secure quantum information from 3 ground stations to the satellite here. So it's actually the most secure video call, but it's kilobytes per second rate, okay? So if you think about it, that is your cellular network in the 1970s, okay? Definitely not the way I want to watch my Netflix. So I'm happy to compromise there, okay? So it's nowhere near what we'll use for our Netflix, but maybe someday we'll get there. I mean, this is a personal favorite of mine. It's an Australian company. So quantum scrambling, what do I mean by that? We store information in the cloud all the time. What if somebody hacks that cloud? What if somebody actually steals the information from the cloud? Then suddenly my information is not secure anymore. So Quintessence Lab in Australia scrambles that information in a truly quantum random way, okay? Before you save that to the cloud. So even if somebody steals the information in the cloud, to them it would look random. They wouldn't know what that is. Because to descramble that, you have to go to where you scramble that information. Usually a law firm or some, I don't know, secret KFC recipe or, you know, things like that. Okay? So, yeah, that's I think I've fulfilled my promise now. So, difference, experiments, never gentle, quantum states, they're really very peculiar. You can hide your ignorance using quantum information. And we are far off from the promise of quantum technology, but I think we're getting there quickly. It's a very complex problem, lots of challenges, open for, very many young people, young and old, who wants to a challenge. I think it's very about time. Okay, thank you.
Thank you, Jacqui, for a fantastic talk, delving into many of the intricacies, but also the big picture of the quantum information world. We are going to take some questions now. We've got a few minutes left. So if you have questions, you can either write them down or you can tweet them through. We've already had a couple of questions come through here. And our wonderful host will come around and collect those questions now and bring them up the front. Meanwhile, next month we will, of course, be back and we'll be meeting a UQ psychology expert who has been comparing the developmental stage progress of chimpanzees with that of human children. So, you know, you can really start to think about your life decisions and your family. So it'll be a really fantastic talk. I would really encourage you to come along to that. I'm going to go to questions. We'll start with Twitter while these guys are bringing up some of the first questions. First question here on Twitter is from Jennifer. You ready to go?
Yeah.
Great. First is Jennifer, who asks, when will it be possible for me to go to the local computer store and buy my own quantum computer?
Okay. Actually, now, if you want one, you can access one remotely. IBM Quantum Experience is free. The 16-qubit machine, I think, is free. You just need an account, and you can play with that quantum computer. I don't think you'd want to put it in your house because these are superconductors. You really need cooling for them. They are colder than outer space. So there's a big investment if you want them in your house. But you can have that quantum experience now. Yeah.
What kind of experiments might you test out on the 16 qubit?
On this, like you can test like all sorts of quantum games. Like this experiment that we did at UQ, you can probably do it there. You can have your own like BB84 protocol, I guess. Like yeah.
Weekend
Different
project,
games.
everyone.
Yeah.
Okay, we've got another question here, which is, how big do things have to get before quantum mechanics doesn't apply?
Oh, that's a very good question. How big do things have to get? It depends, right? If you have a block as big as this stage, but I put it to absolute zero, that would be quantum because none of the things would be moving, right? So I think it's a very complicated question. I don't think size matters, although, of course, we think... Okay, so the size matters because the bigger the size is, the more you interact with an environment. And quantum systems, they don't like interacting with the environment. But if you can keep that interaction with the environment to a minimum, I think you can have as big as you want. So the biggest that we've had in our labs are buckyballs, like 60-atom carbon molecules. So with engineering, you can do it, but it's hard. Yeah.
Great. Okay, we have another question here, perhaps sort of building on some of these things, which is, what do you think the next big breakthrough in quantum research will be?
I don't know, actually. I think now people are very focused on really taking the technology forward because we are getting a lot of momentum from the noisy intermediate quantum computers that we have. So we want to show that this is actually useful for something. Like what I wish we could show with what we have right now is that really we can tell you which way you should put your molecules together for it to work. Like I think the application of quantum computer would be for simulating molecules. Yeah. I mean, quantum communication is of course like the promise is hacker-proof communication, right? But yeah, it's going to happen. It already happens, kilobytes per second.
Right. Okay, I got a question here from Dave, who asks, are there likely to be other quantum algorithms like Grover or Schur, and any ideas what, if so?
So far, I've only really read these two. They are the most popular. Probably there are things out there that we haven't discovered yet. But also note that, like the Shor's algorithm is good because we haven't found a smarter way to factor our numbers in the classical computer. Like tomorrow, maybe a computer scientist would say, well, I can factor numbers more efficiently than how we do now, right? So then there's sort of a race, really, right? So yeah, I don't know. Like the computer scientists would probably know better.
All right, got one more question for you from someone who clearly doesn't work in a university environment, but if you had an infinite budget, what experiment would you conduct?
If I had an infinite budget, okay. So all the work we see now, it's all qubits, right? Qubits, two-state. Now, I'm a bit of an outsider in the sense because I like qubits. Qubits because nature gave us qubits. Your atoms, they have more than 2 levels. Light, it has more than 2 colors. It has more than 2 shapes. Why do we limit ourselves to 2? And the answer is because we are familiar with 2. 2 has worked for classical information. But I think if we really are smart enough and we have all the money in the world that we can control all those d quantum levels, we can actually do so much more. So if I had money, there's actually a proposal for universal qubit quantum computation. I'm going to go for that.
Brilliant.
Yeah.
Well, BrisScience will get crowdfunding and we'll see what we can do. But that's a wonderfully inspiring note to finish on. Could you please put your hands together for our fantastic speaker, Jacqui, and join us for some food and drink outside?
Okay. Oh, I get a gift. Thank you. Okay. Thank you.
Don't forget to join us next month.